For more than 2,000 years, a silent engineering triumph has endured beneath collapsed temples, harbor walls, and broken imperial cities. Roman concrete. Not because it was mysterious or mythical, but because it was precise, intentional, and astonishingly advanced. While modern concrete can fail in just a few decades, the Romans engineered a material capable of surviving seismic shocks, saltwater corrosion, enemy sieges, and the slow, relentless erosion of time. Standing in front of structures that still hold their weight after 20 centuries forces a single question. How did they do this without the tools and formulas we rely on today? To understand the answer, we must step into a world where engineering was not a profession. It was survival. Rome grew not through conquest alone, but through infrastructure that connected mountains, stabilized coastlines, and unified millions under a single logistical system. Their concrete was not merely a construction material, it was a strategic asset, a statement of permanence. It allowed emperors to build harbors where none should exist, temples that defied architectural limits, and domes that remain unparalleled in scale. Behind every triumph stood a formula refined by necessity, experimentation, and genius. But this story is far from simple. Roman concrete was not one recipe, it was dozens, each tailored to geography, purpose, and stress. Volcanic ash from Pozzuoli, lime burned in controlled conditions, aggregates selected by density and fracture pattern, all combined with a chemical intelligence that modern science only recently began to decode. What they built wasn't just durable, it was reactive, evolving, strengthening itself over time. This episode reveals how Rome engineered longevity using ingredients still accessible today, and why we lost this knowledge for centuries. To grasp the scale of their achievement is to confront the limits of our own. If you appreciate deep historical engineering like this, consider liking and subscribing. Roman concrete was never an accidental achievement. It emerged from centuries of experimentation across a rapidly expanding empire that faced every geological challenge imaginable. From the volcanic fields of southern Italy to the salt-heavy winds of the Mediterranean, Roman builders encountered environments that demanded different engineering responses. Their solution was not a single formula, but a system, a family of concretes, each designed with purpose, adapted to local materials, and refined through constant observation. These mixtures were chosen not only for strength, but for longevity, stability, and their ability to interact with the world around them. What makes this material remarkable today is not merely its survival, but its behavior. Modern studies reveal that Roman concrete doesn't simply endure time, it responds to it. Under microscopes, researchers find crystalline structures forming within ancient cracks, evidence of ongoing mineral reactions that reinforce the material rather than degrade it. This was a construction medium that evolved. Its chemistry remained active for centuries, slowly strengthening the very walls and foundations that empires rose and fell around. In a sense, Roman engineers built structures that learned to maintain themselves. To understand the significance of this, we must remember that Rome engineered at a scale few civilizations attempted. Their roads, harbors, aqueducts, warehouses, and temples supported millions of people across 3 continents. Stability was not a luxury, it was fundamental to administration, trade, and military logistics. Concrete capable of enduring earthquakes, storms, and seasonal extremes allowed Rome to project power far beyond what timber or cut stone could offer. Their cities were not just inhabited, they were engineered systems. This episode looks beyond the myths and simplifies nothing. It examines the substances themselves, the geological logic behind them, and the decisions that shaped their evolution. To understand Roman engineering is to understand how knowledge, resources, and ambition converged into a material unlike any other of its age. Long before Roman engineers could refine their concrete, they first had to understand the landscapes that supplied its ingredients. The Italian peninsula was a mosaic of geological zones, volcanic plains, limestone mountains, coastal marshlands, and river-cut valleys. Each region offered materials with radically different properties. Pozzolanic ash from Campania reacted chemically with lime, creating compounds of exceptional durability. Limestone from the central mountains calcined into a lime that bonded aggressively with aggregates. Rivers carried stones with fracture patterns ideal for load distribution. Rome did not merely use what it found, it learned to read the terrain. This was the foundation of their engineering philosophy. Materials dictated method. The earliest Roman builders did not yet comprehend the chemistry behind these materials, but they understood their behavior. They observed how volcanic ash hardened on contact with water, how certain limestones fractured into smooth, workable pieces, and how river stones held steady under pressure. These observations formed an empirical knowledge base that spread through military campaigns, road construction, and the constant rebuilding of early settlements. Every conquered region taught Rome something new about the earth. Knowledge accumulated not in manuscripts, but in walls, floors, and foundations. By the 3rd century BCE, Rome had begun standardizing the use of pozzolana, the volcanic ash that would become the heart of their concrete innovations. Builders noticed that structures using this ash resisted cracking far better than those relying solely on lime and sand. Harbors built with it stood firm against waves that pulverized traditional stone blocks. Even inland structures benefited from its slow crystallization process, which increased material strength as years passed. Without formal chemistry, Rome had stumbled upon one of the most effective mineral binders in ancient history. As Roman engineers experimented with pozzolana, they refined the ratios of lime, aggregate, and ash. Too much ash produced brittle mixtures. Too little reduced its reactive benefits. They developed combinations tailored to specific uses: dense mixes for foundations, lighter mixes for vaults and upper walls, and uniquely reactive mixes for marine structures. These refinements were not theoretical. They were tested through constant construction. Rome was expanding rapidly, and each new building, fortification, or warehouse provided a chance to iterate. Construction became research. One of the most transformative discoveries came from observing how water interacted with volcanic ash. Instead of weakening the mixture, seawater activated it. Marine concrete began forming rare minerals, like aluminous tobermarite, that modern engineers struggled to produce in laboratory settings. These minerals grew over decades, binding the aggregates more tightly and enhancing structural resilience. The Romans may not have grasped the molecular processes at play, but they recognized the outcome. Harbors built with pozzolanic concrete became almost indestructible. The practical implications of this discovery were immense. Traditional coastal structures required constant repairs, especially after storms. But Roman harbors, often built in hostile environments, endured with minimal upkeep. This gave Rome a logistical advantage. Stable maritime infrastructure meant goods moved reliably, fleets could dock safely, and coastal settlements could flourish without fear of structural collapse. Engineering became strategy. Materials became instruments of imperial control. As Rome expanded, its engineers traveled with legions, observing new terrains and adapting concrete mixtures accordingly. In regions with poor natural pozzolana, they identified substitutes: crushed ceramic, metamorphic dust, or ashes from different volcanic sources. Each adaptation maintained the principles of pozzolanic reaction, even if the ingredients varied. This mobility of knowledge allowed Roman engineering to function universally across the empire. Concrete was not a local craft, it was a transferable technology. The role of lime in Roman concrete also evolved. Early mixtures used roughly calcined lime that reacted unpredictably. Over time, Roman kilns became more controlled, producing lime of higher purity and consistency. This enhanced the binding phase of concrete and reduced the risk of internal flaws. Kilns themselves became feats of engineering, optimized to maintain stable temperatures and produce uniform material. The improvement of one component strengthened the entire system. Aggregates, often overlooked in casual descriptions of concrete, played a crucial role. Roman engineers selected them by shape, density, and fracture behavior. Angular stones bonded better with mortar, while rounded stones were used to lighten loads. Large fragments increased compressive strength, while smaller ones filled microgaps. There was nothing random about Roman aggregate selection. It was a deliberate craftsmanship that modern construction often overlooks. By the time Rome reached its imperial height, its concrete was not merely a material, but a legacy encoded in stone. Every improvement, every refinement, every regional adaptation had been layered into a system that no single engineer invented and no single generation controlled. Roman concrete was the accumulated intelligence of a civilization learning from the earth itself. As Roman concrete matured into a strategic material, its most defining characteristic emerged: adaptability. Unlike modern concrete, which often follows standardized proportions, Roman concrete was intentionally flexible. Engineers could redesign mixtures on the fly, responding to environmental pressures, structural demands, and available resources. This adaptability turned concrete into a universal tool. It could be poured into wooden forms for vaults, stacked in layers for thick fortifications, or shaped around irregular landscapes where cut stone would have failed. To Roman builders, concrete was not a compromise. It was liberation from the constraints of traditional architecture. One of the clearest demonstrations of this adaptability appears in the construction of Roman vaults and domes. Stone vaults required perfect geometry and immense material precision, but concrete allowed forms to become fluid and expansive. The builders constructed wooden frameworks, then poured concrete in layers, each with a slightly different aggregate size and density. Heavier mixes anchored the lower sections, while lighter mixes, often containing volcanic pumice, were used higher up to reduce weight. This gradient approach can be seen most famously in the Pantheon, where the concrete becomes progressively lighter as it rises, culminating in a dome that still holds the world record for an unreinforced span. Concrete also gave Rome the power to construct at unprecedented speeds. While stone cutting required meticulous shaping and transportation, concrete could be mixed near the building site and applied continuously. Entire walls could be raised in days rather than weeks. For military campaigns, this efficiency was invaluable. Temporary forts, storage facilities, and even bridges were erected rapidly, enabling legions to maintain supply lines and strategic mobility. Concrete turned Rome into a civilization capable of reshaping landscapes on command. But speed did not overshadow precision. Roman builders understood that the success of concrete depended heavily on preparation. Aggregates were washed to remove dust that could weaken bonds. Lime was slaked carefully to prevent dangerous reactions within walls. Ash was stored in dry conditions to preserve its reactivity. The mixing process itself required skill, as workers gauged proportions by texture and behavior rather than strict measurement. A well-mixed batch of concrete was recognized by its cohesiveness and how it clung to tools. Craftsmanship was embedded in every step. Foundations reveal another layer of Roman sophistication. Instead of relying solely on concrete, engineers often combined multiple strategies: compacted earth, layers of gravel for drainage, timber piles in wet environments, and concrete poured strategically to bind the system together. This hybrid approach allowed structures to adapt to shifting soil, heavy loads, and environmental stresses. The foundations of Roman bridges, in particular, demonstrate a nuanced understanding of hydrodynamics and land behavior. Concrete was never used blindly. It was integrated into a broader engineering philosophy. In coastal environments, Rome reached a pinnacle of innovation. Marine concrete made with pozzolana that reacted vigorously with seawater allowed harbors to be constructed even in turbulent conditions. Engineers built wooden cofferdams, poured concrete underwater, and allowed it to set in place, a technique centuries ahead of its time. These maritime structures became lifelines for trade, military logistics, and urban expansion. Their survival today, despite constant wave action, remains one of the most striking testimonies to Roman engineering intelligence. Urban planning also benefited immensely from concrete. Insulae, multi-story apartment blocks, relied on concrete cores and walls to reach unprecedented heights for ancient cities. Wealthy districts featured concrete foundations supporting elaborate stone facades, while poorer districts depended on concrete for affordable, quickly built housing. Concrete unified Rome's urban fabric, enabling dense cities that were structurally stable and economically feasible. It allowed Rome to scale upward, not just outward. Even infrastructure relied on concrete in subtle yet essential ways. Roadbeds incorporated concrete layers that resisted compression and water infiltration. Aqueduct channels were lined with waterproof concrete called opus signinum, made from crushed tiles and lime, ensuring clean water delivery across vast distances. Storage facilities, granaries, and military warehouses used concrete floors that resisted moisture and pests. Concrete quietly enabled the administrative and logistical systems that held the empire together. By the late empire, concrete had become more than a material. It was an identity. Visitors from other cultures wrote about Rome's buildings with astonishment, noting their scale, endurance, and unusual texture. To walk through a Roman city was to encounter volumes of space, curves of architecture, and feats of engineering unavailable elsewhere. Concrete allowed Rome not only to build structures, but to express imperial ambition through architecture. It carved Rome's presence into landscapes across continents. What makes Roman concrete extraordinary is not a single innovation, but the convergence of knowledge, adaptability, and relentless experimentation. Rome engineered for the long term, building structures intended to outlast generations. 2,000 years later, their success is still visible in every surviving vault, pier, dome, and harbor that stands against the erosion of time. Understanding why Roman concrete endured for millennia requires looking beyond its ingredients and focusing on its internal chemistry. an evolving chemical landscape that transformed each structure into a living system. When Roman engineers mixed lime with volcanic ash, they initiated reactions that would continue long after construction ended. Modern concrete behaves predictably in early stages and then stabilizes. But Roman concrete kept strengthening decades, even centuries after the material set. This long-term reactivity became one of its greatest advantages, as microfractures triggered new mineral formations that reinforced the structure rather than weakened it. At the heart of this process was the interface between lime and pozzolana. When seawater or rainwater infiltrated the material, it did not erode it. Instead, it dissolved small amounts of lime, which then reacted with volcanic components to form crystalline bonds. One of the most remarkable of these bonds was aluminous tobermorite, a mineral found in extremely rare natural formations, but common inside Roman marine concrete. Its crystal structure is elongated, interlocking, and capable of providing exceptional tensile and compressive strength. Modern engineers have studied it extensively, recognizing that replicating it could revolutionize contemporary construction. The Romans, of course, did not know the mineral's name, but they understood the effect. They observed that harbor walls hardened over time, even under constant wave impact. They noticed that structures incorporating certain volcanic ashes resisted cracking or spalling. Over generations, builders intentionally sought ash sources that produced the most durable mixtures. This empirical refinement created a material that modern scientists admire for its complexity and resilience. Where many ancient construction techniques relied on craftsmanship alone, Roman concrete relied on a synergy of craft and chemistry. Another crucial factor in Roman concrete's longevity was its ability to accommodate stress. Modern concrete often relies on steel reinforcement, but steel is vulnerable to corrosion. When corrosion begins, the expanding metal fractures the surrounding concrete, accelerating deterioration. Roman concrete, by contrast, had no embedded metal. Instead, it relied on a mixture whose internal structure could redistribute stress gradually. The presence of porous aggregates, varied grain sizes, and the gradual formation of binding minerals allowed the material to adjust to pressure, temperature changes, and seismic movement without catastrophic failure. This flexibility was especially useful in maritime environments. Roman harbors were built in dynamic zones where waves, tides, storms, and shifting seabeds created constant mechanical stress. Instead of resisting these forces through rigidity alone, Roman concrete adapted to them. Cracks that might have spread in modern materials instead triggered mineral formation, effectively turning weaknesses into reinforcement sites. The concrete reacted to stress not by failing, but by reorganizing its internal bonds. It was, in a sense, self-optimizing. The internal structure of Roman concrete also reveals a sophisticated understanding of aggregate selection. Engineers included large chunks of tuff, pumice, and broken ceramic to create a composite that managed thermal expansion and contraction. These inclusions acted like shock absorbers, diffusing stress across the mass. In marine concrete, porous volcanic stones allowed seawater to penetrate in controlled ways, initiating beneficial reactions without compromising structural integrity. The Romans did not need microscopic analysis to recognize performance. They watched how materials survived the seasons, and they built accordingly. One of the most intriguing aspects of this long-term chemistry is that it challenged a core assumption of modern engineering, that uniformity equals strength. Modern concrete is carefully standardized, but this uniformity is precisely what makes it vulnerable. Weaknesses propagate quickly through a homogeneous material. Roman concrete, by contrast, was intentionally heterogeneous. The varied particle sizes, mineral inclusions, and layered textures created a complex internal architecture that slowed crack propagation. Differences within the material became sources of strength rather than defects. Research has also shown that the lime used by the Romans often remained partially unreacted within the mixture. These lime clasts, once dismissed as signs of poor craftsmanship, are now understood as reservoirs for self-healing reactions. When microcracks formed, water dissolved the lime, creating a local recrystallization zone that sealed fractures. The presence of these clasts indicates intentionality. Rome was engineering durability at both macro and micro scales. What appeared rudimentary was, in truth, an innovation unmatched for centuries. Examining surviving structures reveals a final insight into Roman concrete's endurance, its ability to maintain cohesion even as individual components aged differently. The layered aggregates, mineral veins, and hydrating lime all matured at distinct rates, creating a time-staggered strength profile. Instead of weakening as components aged, The structure redistributed forces across newly formed crystalline bonds. In effect, Roman concrete grew stronger, not despite time, but because of it. Rome built monuments, harbors, and cities with the expectation of permanence. Their concrete honored that ambition through a chemistry that modern science is still trying to fully decode. In every fragment examined under a microscope, one finds evidence of a civilization that engineered not just for function, but for centuries beyond its own. The triumph of Roman concrete becomes even clearer when compared to other ancient building materials. Civilizations across the world developed remarkable techniques: Egyptian limestone blocks, Greek marble temples, Incan polygonal masonry, but none achieved the same combination of scale, speed, adaptability, and longevity. Stone structures required extensive quarrying, specialized labor, and precise carving. They could last millennia, but only under stable conditions and with enormous human investment. Roman concrete, by contrast, democratized durability. It allowed ordinary laborers, under the guidance of skilled foremen, to construct resilient structures at unprecedented rates, reducing dependence on elite craftsmen without compromising strength. What made Roman concrete revolutionary was its ability to act as both structure and binder. In Egyptian pyramids, stone blocks carried the load. In Greek temples, marble beams bore weight through compression. In Mesopotamian architecture, mud brick required constant upkeep. Roman concrete eliminated these constraints. It could form arches, vaults, domes, retaining walls, and underwater foundations. It turned architectural curves, which were historically difficult, into practical engineering tools. The transition from post and lintel construction to vaulted spaces reshaped how Romans inhabited buildings, allowing larger interior volumes, controlled lighting, and more sophisticated acoustics. Concrete became the medium through which architectural imagination expanded. One of the clearest demonstrations of this shift is the evolution of the Roman bathhouse. Early bathing facilities resembled simple Greek structures, but as concrete advanced, baths transformed into monumental complexes with vast vaulted ceilings, elevated floors heated by hypocaust systems, and intricate water channels. Concrete enabled engineers to create expansive, open rooms with stable temperature control, a feat nearly impossible with stone beams or timber roofing. The baths of Caracalla and Diocletian remain among the most impressive examples of large-scale interior engineering in the ancient world, made possible by a material that responded predictably to thermal and moisture stresses. Concrete's utility extended into engineering challenges far beyond architecture. Consider the construction of cisterns and reservoirs. Water storage was critical for Rome's survival and expansion, and traditional materials often leaked, cracked, or eroded. Concrete lined with waterproof additives allowed cisterns to maintain structural integrity while resisting hydrostatic pressure. Many of these reservoirs remain operational today, quietly storing water in rural Italy and North Africa. Their durability illustrates how Roman engineers approached infrastructure not as temporary solutions, but as long-term investments meant to support populations for generations. Even fortifications benefited from concrete's versatility. While stone walls dominated earlier periods, Roman military engineers frequently combined stone facing with concrete cores to create fast-rising, highly resilient defenses. This hybrid method allowed fortresses to withstand siege engines, vibrations from rams, and repeated impacts without collapsing. In frontier regions like Britain and Germania, concrete enabled rapid construction of defenses in remote landscapes. It provided the empire with a logistical advantage that magnified the strength of its legions. Every wall built with concrete enhanced Rome's ability to maintain borders and control territory. Roads, too, became more efficient with concrete. The famed Roman roadbeds were not merely stone pavements. Beneath them lay carefully layered substrates that incorporated concrete or concrete-like mixtures to resist water infiltration and distribute weight evenly. These innovations reduced maintenance costs, improved travel speed, and ensured reliable movement of goods and troops. The longevity of some road sections, still visible and usable today, reflects a sophisticated understanding of load distribution long before modern civil engineering formalized such principles. Urban development further highlights concrete's transformative power. Housing density increased without compromising safety, and large administrative buildings could be erected near markets, forums, and ports. Concrete allowed multi-story structures, something rare in previous civilizations. The insulae, while sometimes criticized for safety issues unrelated to concrete itself, demonstrated a scalable building model that anticipated modern apartment complexes. Wealthy homes integrated concrete with luxury finishes, hiding the material beneath marble veneers while benefiting from its stability and moisture resistance. As Rome's architectural vocabulary expanded, concrete also became a medium for artistic expression. Decorative reliefs were molded directly into walls. Niches for statues were shaped without requiring carved stone. Complex spatial arrangements could be created without worrying about block alignment. Engineers and architects collaborated to design environments that felt unified rather than assembled. The material blurred the line between engineering and artistry, enabling Rome to project cultural identity through form and structure. Ultimately, the rise of Roman concrete marks one of the most significant transitions in the history of architecture and engineering. It replaced the limitations of traditional materials with a system capable of responding to environment, purpose, and ambition. It democratized monumental construction, allowing cities to grow, fortifications to expand, and public works to flourish. Through its adaptability and strength, it elevated Rome from a regional power to an infrastructural titan. The material's endurance is not only physical, but symbolic, a testament to a civilization that built not for the moment, but for the ages. If the Romans mastered the chemistry of concrete, they equally mastered the logistics that made its widespread use feasible. Producing lime required enormous quantities of fuel, stone, and labor. Transporting volcanic ash demanded coordinated supply chains across land and sea. Aggregates had to be quarried, sorted, and delivered to construction sites in steady rhythms. None of this happened by accident. Rome built a logistical empire to support its architectural empire. Kilns were placed strategically near limestone sources. Roads connected quarry sites to ports. Barges transported heavy materials down rivers, and urban storage depots ensured a constant flow of supplies. Concrete was possible not only because the formula existed, but because Rome built the infrastructure to sustain it. At large-scale construction sites, organization dictated output. Workers known as fabri prepared tools, while calcarii managed lime kilns, ensuring consistent temperatures for proper calcination. Caementari, specialized concrete workers, prepared mixtures based on instructions from master builders who understood how different combinations behaved under stress. These teams operated in shifts, maintaining a continuous workflow so that layers of concrete could bond effectively. The process required discipline and coordination, making construction a synchronized operation rather than a simple gathering of laborers. Rome's engineering success depended as much on management as on materials. Urban centers exemplified this system's speed and efficiency. Apartment blocks, bridges, and administrative buildings often rose simultaneously within compact districts. With concrete, builders were no longer constrained by the slow precision of stone carving. They erected wooden frameworks, filled them with concrete, and moved upward in rapid succession. The beating rhythm of mixing, pouring, and leveling echoed through Roman streets. Clay pipes carried water for mixing, mobile kilns operated nearby, wagons delivered aggregates. Construction was a continuous motion machine. Where earlier civilizations built slowly, Rome built continuously. The empire's military frontiers further illustrate the power of concrete as a logistical asset. Engineers accompanying legions could construct bridges, granaries, and defensive towers in record time, enabling campaigns to move rapidly and efficiently. In foreign territories where stone was scarce or unsuitable, concrete allowed Romans to replicate familiar structures using local materials supplemented with ash transported from the Mediterranean. This consistency across regions reinforced imperial authority. A Roman fort in Britain shared architectural DNA with one in Judea or North Africa because the same engineering logic shaped them all. Harbor construction required yet another level of logistical sophistication. Building underwater demanded precise timing, specialized equipment, and coordinated labor. Wooden forms were assembled on barges, lowered into position, and filled with concrete mixtures designed to react with seawater. Ash shipments were planned months in advance to coincide with favorable tides and weather. The Romans even developed hydraulic tools to support underwater work, including cranes and lifting machines adapted for aquatic environments. Every successful harbor was the result of a finely tuned supply system that acted as an extension of engineering intelligence. What made this logistical mastery even more extraordinary was its scalability. Small towns used simplified systems, while major cities relied on intricate supply networks. Rome itself required enormous volumes of materials for its baths, forums, aqueducts, and theaters. Quarrying companies, kiln operators, river transport crews, carpenters, and concrete specialists formed a coordinated chain that fed the city's constant appetite for construction. This network was so robust that it functioned for centuries, even during political instability. Concrete bound not only structures, but the empire's socio-economic engine. Another dimension of logistics lay in Rome's administrative recording and standardization practices. Although they lacked modern engineering documents, Roman builders maintained practical knowledge through repeated use and observation. Foremen passed techniques across generations. Kiln managers tracked fuel consumption and stone quality. Surveyors documented land gradients and foundation behavior. These collective observations created an empirical knowledge tradition that compensated for the absence of formal scientific texts. Rome engineered through repetition, sharpened by experience. The transportation system itself, rivers, roads, and sea lanes, was deliberately shaped to serve the needs of construction. Roads paved with concrete layers allowed heavy loads to move efficiently. Rivers transported ash and stone from inland quarries to coastal cities. Sea routes connected volcanic regions to harbors scattered across the empire. In this integrated landscape, logistics became a force multiplier. Roman engineering was inseparable from Roman mobility, each reinforcing the other in a cycle of expansion. Yet perhaps the most revealing aspect of Rome's logistical success is how seamlessly it adapted to the empire's growth. As new territories were annexed, new material sources were identified and integrated. As cities expanded, supply chains scaled with them. The system remained dynamic, adjusting to climate, geography, and political changes. This adaptability mirrored the flexibility of the concrete itself, a material that changed and improved over time. Rome did not merely build with concrete, it built a civilization around the ability to use it. Among the countless structures built across the Roman world, several stand out as definitive demonstrations of concrete's capabilities. Projects so ambitious, so technically refined, and so enduring that they continue to reshape our understanding of ancient engineering. The Pantheon, with its vast, unreinforced dome, is often cited as the empire's pinnacle of architectural achievement. Yet its brilliance lies not in its size alone, but in the careful tuning of concrete composition, layer by layer. At the base, engineers used dense aggregates like basalt to provide compressive strength. Near the oculus, they incorporated lightweight pumice to reduce weight without sacrificing structural integrity. This gradient engineering created a dome that distributes stress evenly, preventing catastrophic cracking even after nearly 2,000 years of environmental fluctuations. The Colosseum tells a different story, one of speed, repetition, and modular design. Though its exterior famously features travertine stone, the majority of its internal structure relies on concrete vaults and radial walls. This allowed builders to construct identical support modules rapidly, enabling the enormous amphitheater to rise far faster than a comparable stone structure. Concrete provided the flexibility to create curved corridors, angled ramps, and complex load paths that guided tens of thousands of spectators safely through the building. Its survival through earthquakes, fires, and centuries of repurposing is a testament to its robust internal skeleton of concrete. Aqueducts showcase yet another dimension of Roman engineering: hydraulic precision. While their elegant arches often attract attention, many aqueducts relied heavily on concrete channels lined with waterproof mixtures such as opus signinum. This specialized concrete, incorporating crushed pottery, resisted water infiltration and prevented mineral buildup that could clog the system. Concrete also stabilized underground tunnels and supported siphon systems that carried water across valleys. Without these innovations, Rome's urban centers could not have sustained their enormous populations. Harbors like Caesarea Maritima reveal concrete's unmatched performance in marine environments. To build them, engineers filled wooden forms with volcanic ash-based concrete and lowered them underwater, where seawater triggered a chemical reaction that strengthened the mixture over time. The resulting harbor moles, breakwaters, and foundations remain some of the most resilient maritime structures ever created. Modern port engineers still study them for insights into long-term resistance to saltwater degradation. These innovations allowed Rome to maintain reliable naval logistics and trade routes across the Mediterranean, reinforcing the empire's economic stability. Roman bridges further highlight the versatility of concrete. Many utilized stone arches but relied on concrete cores to bind awkward shapes, fill irregular cavities, and distribute loads more effectively. Bridges like Alcantara and Fabricius remain operational today, their durability enhanced by concrete foundations that anchor them securely to riverbeds. The ability to pour concrete around shifting stones or into challenging geological settings gave Roman engineers tools unmatched by earlier civilizations, transforming river crossings from engineering obstacles into strategic assets. In residential and commercial construction, concrete allowed architects to design insula, multi-story apartments that housed the growing urban population. Concrete cores provided stability while allowing for flexible interior layouts. Decorative veneers often disguise the concrete beneath, demonstrating that Romans valued both structural performance and visual refinement. These buildings, though sometimes vulnerable to fire due to timber floors, represented a major leap in urban density and vertical expansion. Without concrete, Rome's cities could not have reached their immense scale. Thermal engineering in bath complexes further demonstrates concrete's adaptability. Hypocaust systems required floors that could tolerate continuous heating without cracking or buckling. Romans solved this by using mixtures designed to endure thermal cycling. Concrete suspended floors, supported on small brick pillars, allowed hot air to circulate beneath. Vaulted ceilings of concrete distributed heat throughout the structure. The result was a controlled thermal environment on a scale unmatched until modern HVAC systems. Even warehouses, structures built for practicality rather than beauty, benefited from concrete's precision and resilience. Horea, or storage facilities, used concrete floors to resist moisture migration, preserving grain and other commodities for long periods. Their thick concrete walls maintained stable interior temperatures and protected goods from pests. The efficiency of these storage systems supported Rome's ability to feed its cities and armies, demonstrating that the material's impact extended beyond monumental architecture. One cannot overlook the engineering of temples and basilicas, where concrete enabled vast interior spaces unobstructed by columns. The Basilica of Maxentius, for example, features concrete vaults so large that they rival Renaissance cathedrals in scale. These spaces redefined public architecture, allowing social, commercial, and judicial activities to occur within unified environments sheltered from the elements. The combination of structural innovation and architectural grandeur set new standards for public buildings worldwide. Across all these examples, a single principle emerges. Roman concrete was not merely a construction material, but an enabling technology, a foundation upon which the empire built its infrastructure, identity, and longevity. Whether in harbors battered by storms, domes that challenged gravity, or aqueducts that carried life-sustaining water across continents, concrete served as the invisible framework behind the Roman world. Its omnipresence in both monumental and utilitarian structures demonstrates its unparalleled versatility and enduring value. As modern researchers analyze Roman concrete through microscopes, X-ray diffraction, and high-resolution imaging, they uncover details that reframe our assumptions about ancient engineering. The material's complexity is not accidental. It reflects centuries of empirical refinement and region-specific problem-solving. The Roman world was vast, its climate unpredictable, and its geography diverse. Each environmental stress, earthquakes, salt spray, seasonal flooding, coastal erosion, forced builders to adapt formulations. The result was not a single recipe, but a multi-generational engineering tradition. This tradition shows that Rome's real innovation was not merely chemical, it was organizational and intellectual, built on the transfer of knowledge across an empire. The rediscovery of Roman concrete in modern times was slow and at first dismissive. For centuries, engineers assumed it was inferior due to its coarse appearance and irregular texture. Only recently did scientists begin to realize that those irregularities, lime clasts, porous aggregates, variable grain sizes, were deliberate features, not defects. These seemingly crude inclusions serve as stress absorbers, chemical reservoirs, and microstructural anchors. What looked primitive proved strategic. The mismatch between ancient intentions and modern assumptions reflects how thoroughly Rome understood the behavior of materials without formal theory. Today, Roman concrete has become a case study in sustainable engineering. Modern concrete, despite its uniformity, suffers from limited lifespan. Steel reinforcement corrodes, moisture intrusion accelerates cracking, and thermal cycles create internal stresses that eventually cause structural failure. Roman concrete avoids these vulnerabilities by embracing heterogeneity and mineral evolution. Its chemistry remains active, enabling microcracks to seal themselves over time. This capacity for self-maintenance has attracted global interest as engineers seek alternatives to carbon-intensive building practices. Learning from Rome is no longer academic curiosity. It is a potential path forward. Marine construction is where the contrast becomes most striking. Many modern harbor structures require constant repair, yet Roman harbor walls continue to resist ocean forces after 2 millennia. Engineers examining samples from sites like Pozzuoli and Caesarea observe mineral formations rarely found in nature, indicating long-term chemical reorganization. These discoveries challenge the notion that longevity depends solely on initial strength. Instead, Rome engineered materials that improved with age, a concept modern material science has only recently begun to explore with self-healing concretes. Rome achieved the effect without synthetic polymers or laboratory conditions, relying entirely on volcanic geology and careful craftsmanship. The durability of Roman concrete also reveals insights into the empire's worldview. Roman builders did not construct for temporary glory or for personal attribution. Many buildings, including aqueducts and storage complexes, were anonymous. They served functions greater than individual fame. The system valued longevity because longevity translated into stability, economic, political, and cultural. Concrete became a physical expression of Rome's aspiration to endure beyond the lives of emperors. The fact that its structures remain standing today affirms that the engineering philosophies embedded in the material aligned with the empire's identity. As scientists examine samples from different regions, they find variations that reflect distinct local priorities. In seismic zones, mixtures incorporate aggregates designed to dissipate sudden stresses. In cold climates, concretes include materials that reduce freeze-thaw vulnerability. In desert regions, binders slow hydration to prevent premature setting. These regional adaptations demonstrate a level of environmental engineering that is often underestimated. Rome did not impose universal solutions. It engineered locally while thinking imperially. This flexibility is a hallmark of sophisticated civilizations. Yet the most profound insight lies in how Rome blended innovation with tradition. Concrete rarely appeared alone. It was integrated with stone facings, brick frameworks, wooden scaffolding, and metal clamps. Roman engineering was holistic. Instead of viewing materials as isolated components, they considered how each material complemented another. Concrete acted as the unifying core, a stabilizer that allowed other materials to express their strengths. This integrated thinking resembles modern composite engineering, where multiple substances form systems stronger than their parts. Modern engineers continue to study Roman concrete, not to replicate it exactly, but to understand the principles behind its performance. The volcanic ash used by the Romans came from specific geological deposits with unique compositions. While substitutes exist, none perfectly match the properties of ancient pozzolana. Instead, researchers analyze the underlying behaviors: long-term mineral formation, stress redistribution, heterogeneous bonding, and environmental reactivity. These insights influence contemporary materials science, inspiring research into low-carbon concretes, mineral reactive binders, and alternative reinforcement methods. Rome's legacy thus extends into laboratories as much as it remains preserved in ruins. The survival of Roman concrete challenges our assumptions about technological progression. It forces us to acknowledge that ancient engineers solved problems we still face today: durability, sustainability, and adaptation to environment. Their solutions were shaped by empirical observation and iterative improvement rather than formal chemistry, yet they achieved results that modern materials struggle to match. The Roman world may have vanished, but its engineering achievements remain active participants in today's scientific discourse. Ultimately, Roman concrete stands as one of the most extraordinary intersections of geology, craftsmanship, and strategic thought in human history. It was a material that carried the weight of empires, resisted the violence of nature, and shaped landscapes across continents. Its endurance is a reminder that engineering genius is not the exclusive domain of modernity. In every surviving arch, dome, harbor, and foundation, Roman concrete continues to whisper the same message it has carried for 20 centuries: that strength built with understanding, patience, and adaptation does not fade with time. It grows. Roman concrete endures not simply because its chemistry was remarkable, but because it embodied a philosophy of engineering centered on observation, adaptation, and respect for natural processes. Every structure that still stands today reflects decisions made by builders who understood the behavior of materials in ways that modern terminology only attempts to formalize. Their mastery was not rooted in theoretical models, but in an ability to interpret the earth itself, to recognize what each landscape offered and what each structure demanded. This harmony between material and intention produced a durability that feels almost unearthly when viewed through the lens of contemporary construction. Across thousands of years, storms battered harbor walls, earthquakes shook foundations, empires collapsed, and entire cities were abandoned. Yet the concrete that supported them continued to evolve internally, reorganizing minerals, sealing fractures, and strengthening its bonds. The endurance of Roman concrete is not passive, it is active, dynamic, and ongoing. It demonstrates that longevity is not achieved through resistance alone, but through systems designed to work with time rather than against it. This insight reshapes our understanding of ancient engineering, revealing not primitive trial and error, but a sophisticated, iterative intelligence. In studying Roman concrete, we are not looking backward, we are looking at a path forward. Its survival invites modern engineers to reconsider assumptions, explore new relationships between materials and environment, and imagine construction methods that prioritize resilience over speed. The ruins that dot the Mediterranean are not remnants of a lost world. They are demonstrations of what becomes possible when engineering aspires to outlast centuries. Roman concrete remains, quietly persistent, offering a final lesson. True strength is not a momentary achievement, but a legacy built deliberately and with foresight.